So, let us start this lecture with a thought process that knowledge is more important than the sound understanding. Understanding is more important than mere information. So, if you look at, we have discussed about the thermodynamics spanning over the 3 laws of thermodynamics, first law of thermodynamics, second law of thermodynamics, and the third law of thermodynamics. Also we have discussed in the very beginning the 0th law of thermodynamics. Basically 4 thermodynamic laws we have discussed, we have used it for analyzing the what you call various processes. And in the last lecture we discussed about the availability, or we call it also exergy. In some book you may find also exergy. That will basically tell you that how much potential you are having or a system is having, and I call that exergy basically in the talent of a person, if you consider that way. And we have learnt that also how to what you call characterize a system in looking at the performances. We have discussed about the first law of thermodynamic efficiency, right, that is the thermal efficiency, and then we discuss also second law efficiency, right. And today what we will do, basically we will be looking at how we can apply this first law of thermodynamics for practical problems, right. Of course, we have looked at, and then particularly we will be looking at the power generation. And if you look at, power plays a very important role in modern life, because we are quite dependent on the power, electrical power, mechanical power and other things. And whenever we do that, we need to what you call understand what are the power systems, right. And all the power systems, they work on a thermodynamic cycle, because otherwise we can't get continuously the power, right. And we will be basically looking at power thermodynamic cycles. And if you look at these things, this thermodynamic cycle can be broadly divided in 2 categories. One is the power generation, other is the refrigeration, right. And these 2 systems, if you look at, basically based on the thermodynamic cycles. And the thermodynamic cycles, if you look at, one is the power cycle and other is refrigeration cycle. And power cycle means basically which will be basis by which the engines are being operated. And these engines is, we have already seen, it can be like heat engines basically, and we know that heat engines absorb certain amount of heat from the thermal reservoir or a high temperature source, and then it will be doing certain amount of work, and then it will be rejecting certain amount of heat into the sink. But the refrigeration cycle or the refrigeration system, which operates on a thermodynamic cycle, what we call refrigeration cycle, and it will be basically doing the other way around. It will be absorbing certain amount of heat from the sink, which is at a lower temperature, and with the help of some work it will be giving what you call heat to the high temperature region, right, the source. So, if you look at these engines, basically can be what you call examples, you can think of automobile engines, and then gas turbine engines, rocket engines, and any other things you can think of. As I told that basically these are the heat engine, a device to produce net power by burning off the fuels, right. It may be fossil fuel, it may be nuclear, like kind of fuels, and basically you will be generating heat, and that acts as that thing, and this will be best operated on the thermodynamic cycles. And this heat, and we are basically considering the combustion, that is the burning of fuel, and this combustion can be kind of divided in two categories. One is the internal combustion engine, other is external combustion engine. If you look at your automobile engine, right, is it an external combustion engine or internal combustion engine? Most of you might be riding your automobiles, right? You will be riding your bike, which is powered by the heat engine, right? Yes or no? So, what is that? Is it internal combustion engine or external combustion? The meaning is that, what is the meaning of internal combustion engine? That is basically the combustion or the burning of the fuel will be an integral part of the engine, right? That is internal part of it. And in external combustion engine, you can burn some fuel, and which is not integral part of the engine, and so that we can call it as an external combustion engine, right. So, you might have seen that nowadays there is a split AC, air conditioner, am I right? So, if you look at condenser is outside, okay, and earlier days it was all together, you can say it is a part of that, now it is being separated out. Of course, that is not the same sense what it is. So, can anybody tell me, like automobile engine, which we are using left and right and profusely rather, is an internal combustion engine or external combustion engine? What are the examples of external combustion engine? What are the examples of the internal combustion engine? I think as you people are not saying anything, let me tell you that these automobile engines, that is the piston engines, and your gas turbine engines, which is being used in your aircraft and also for power generation, are basically internal combustion engine. Whereas, if you look at the steam power plant, where you will be using the boiler, right, and that is basically external combustion engine. There are several other external combustion engine, I think I might not have discussed about Stirling engine, which is a very beautiful engine, like that is basically ideally can give you the efficiency of the Carnot engine. That is why a lot of work was going on earlier days, even still people are working on that. That is basically external combustion. What might be looking at what are the advantages and disadvantages of internal combustion engine, external combustion, which will be better? Internal combustion engine or external combustion engine? Of course, that depends on the application and also kind of thing. So, if you look at internal combustion engine will be the working fluid will be all the times not being controlled very well. So, the emissions and other thing will be higher, whereas the external combustion engine you can control it, you can remotely do that thing, and then and there are several advantages, disadvantages. I will not get into it, because internal let me just to tell you one or two. Internal combustion engine, combustor is a part of the engine, so that you can carry anywhere we like, but the external combustion is the combustor will be separate, and then to carry that it will be difficult. So, but however, for power generation, external combustion engine is good, so that you can minimize the emissions and also maximize the energy utilizations. So, that is another big topic, which or a debatable topic rather, to discuss about that. So, if you look at the power cycle, which generates basically the power, it is not the cycle will be generating power, it is the system which is operated on the thermodynamic cycle, which will produce the power, can be therefore, we are labeling this cycle as a power cycle. And power cycle can be broadly divided in two categories. One is vapor power cycle. As the name indicates that vapor will be produced in the things, it might be it is a liquid and then it will be converted into vapor and again it will be converted into liquid pump and then you will get. And in another cycle or a heat engine in which there is no need to have phase change process, like gas will be working on like your automobile engine. Okay. We take the fuel and then like of course the liquid fuel will be converted to gaseous form, but that is not the case. And then you will be basically burning the fuel and then air mixed with air and then you will be working on that. We will be discussing about the gas power cycle in detail. And now of course, we will be discussing about vapor power cycle today. And when you talk about this power cycle, it can be broadly categorized into two, again based on the whether it is a closed cycle or open cycle. As the name indicates, the open cycle means you will be taking some amount of what you call air from the atmosphere, generally we take because it is a cheaper one and easily available, and then you burnt it and also put the exhaust to the what you call into the atmosphere again. Like most of the automobile engines are basically open cycle engines, right. But the closed cycle where the fluid like will be recirculated, it will not be getting out of the engines, it will be remaining as it is, like your refrigerant. If you look at, of course that is not an engine, but it is a refrigerator. If you look at, we use the refrigerant, right, it will be go on recirculating, right. So that is the basically that cycle you can call as a closed cycle, where the fluid won't be getting into out of the system, it will be remaining recirculated, right. So, and the example of the closed system is basically most of the vapor power cycles are closed cycles, right. And open cycle you can think of gas power cycle, but not necessarily always true, okay. That depends upon applications. So, we need to discuss those things. And our objective is basically to analyze the thermodynamic cycle in twofold. One is to design a new cycle, right. Suppose I am not happy with the cycle and then I want to improve that one. Or another one is to improve the existing cycles, because as we had seen in the last few lectures rather, we are interested to find out second law of efficiency to identify irreversibilities, so that we will pinpoint at those things and try to minimize the irreversibility, so that we can basically improve the efficiency of a system or a engine or a refrigerator or any other things. So, that will be helpful, and also we will have some understanding, so that we will get. So, as I told that main interest in this thermodynamic cycle is to determine the thermal efficiency, because that will tell you how good the cycle is, or also how good the what you call the engine is, or the refrigeration system is. And of course, we will always also need to also look at the other performance parameters, like a second law of efficiency we had seen in the last lecture, right, how to determine that, so that we will know to what extent we can achieve the performance. Otherwise, you may be thinking I want to achieve this, but it is not like possible. So, you should know the limit. So, the thermal efficiency, if you look at, is basically we know that the net work output divided by Q in, Q1. Q1 is basically the amount of heat absorbed by the heat engine from the source, that is a high temperature thermal reservoir. And of course, Q2 is the amount of heat which is rejected into the sink, right. So, therefore, this is the things which we will be using in this for analyzing this thermodynamic cycle, and we will be doing that. So, now we will be discussing vapor power cycles, and if you look at vapor power cycles, the steam power plant is being operated based on that. Of course, we may think that what are the other fluids one can think of using. Like steam power plants are being used profusely, particularly not only in our country, in other places. We depend on the coal for generating power, and then steam power plant is being used. Like if you look at something around 70% of the total, maybe a little more, 70 to 75 you can say. Earlier days it was 90% of the power being generated by the what you call burning of coal. So, therefore, there is a lot of scope for that, but what I was asking is little different. I said, is there any other fluid which can be used as a vapor power cycles? Any idea? Of course, now one has to look at the properties. What are those things? Suppose except water, can we use some other fluid? What are the other fluids comes into picture? Any idea? No idea. Okay, let me just tell you, like mercury can be used, and sodium, potassium, and combination of sodium, potassium and other things can be used. Of course, we will not be discussing about that, we will be basically concentrating on the vapor power cycle, that is which is being used basically the steam as the working fluid, and most of the, as I told, the thermal power plant we use the working fluid, and that is water. Water is a benign fluid, say if you look at, when I look at water, I feel it is a very great thing that our earth is having water, otherwise we could have nowhere, but we are spoiling it in the in the process of development. So, if you look at the working fluid is the water, and although the water is of course available plenty, like it is available abundantly, is it so? It is. I mean, if you look at that way, if I look at other things, and it is quite cheap. Of course, it is getting costlier day by day, which is artificial in nature. But then we use it as a closed cycle. Of course, if I use a mercury, as a for generating power, then I cannot afford to make it an open cycle. Why? Because it is toxic, and then it is having lot of problems, like, and it will cause a lot of disease also. So, but whereas, but we use basically closed cycle for steam power plant. Why it is so? I mean, this is just what you call very different kind of things, right? Why it is so? Can anybody tell me any idea? Because we are using clothes and water. I mean, we can just take some water and then take some produce steam, and then after that we just dump into somewhere, like your automobile engines, right? We get some power and then leave as it is. But we do not do that because of fact that that steam power plant requires a large quantity of pure water. See, if you look at the water, and you might be knowing, particularly the water in IIT Kanpur is having a lot of what you call solid contents of the minerals, right? It is testing, if you look at, if you boil it, you will see the scaling is happening on your utensils. Did you do any time? Right, in your room or something, for this thing you will find. So, that scaling will be producing a what you call corroding the blades, turbine blades, and it will be corroding the boilers and other things. So, therefore, it is very difficult to maintain those what you call components. And therefore, we need to use the water which is will be not containing any solid particles and other things, and like minerals which will dissolve in the water. So, therefore, that is the reason why closed cycle is used in the thermal power plants. Otherwise, if I will use the purify like kind of things, then it will be very costly affair if I just leave it. That water which will be used for in this power plant will be quite pure in nature. So, therefore, you will have to cost will be very high. So, let us look at basically the Carnot vapor cycle, because the Carnot is the reference cycle, one can have that. And if you recall, it consists of reversible processes, basically 4 processes like and 2 isothermal process and 2 isentropic process, right. And it has a maximum efficiency when it is operated between high temperature, that is T1, and low temperature T2. So, we can what you call, it can be used as a standard for comparison. That is why always look at that is whether we could achieve that or not. So, let us look at a typical what you call vapor power systems, and which is will be having what you call a boiler, like where you will be using boiling the water and producing the steam and giving certain amount of heat, that is Q1, and which is basically burning the fuel, and then that heat will be transferred to the boiler, right. It is external combustion. You can, if you look at fluid is going in the tubes, and then it will be kind of things. And then this steam will be expanded in a turbine, right, in this turbine, and then of course, it has to and produce some amount of work, like if you look at, this is the work which is shaft work which is produced. And of course, you can connect this turbine to a genset and produce electricity. Okay. And then this condenser, in that when this fluid will go through the condenser, it will be rejecting the heat, let us say Q2 amount of heat, and then again what you will have to do, you will have to compress it such that it can go to the higher pressure, right, and then it will come to that. So, if you look at the processes, that is basically as I told 2 to 3 certain amount of heat is being taken by the fluid from the boiler, right, and then it is expanded, of course, ideally that we are considering for the time being, that is 3 to 4, and where entropy is remaining constant isentropically, and then heat is rejected what you call 4 to 1, and then 1 to 4 is your compression process. So, if you look at, so this is your expansion, if you look at expansion process, and this is isentropic, as I told that entropy is remaining constant this process, and this is your compression, again isentropic, and this is heat addition, right, 2 to 3, and heat rejection is 4 to 1, and temperature is remaining constant, this is isothermal heat rejection, and heat addition also isothermal in the Carnot cycle. Now, if you look at what are the problems we will face if we will use the Carnot cycle. Of course, there will not be any problem for the heat addition, because if the phase change process is taking place, if you keep the pressure constant, the temperature automatically will be constant, there is no problem. Similarly, heat rejection, there will not be much problem of keeping the temperature in a practical sense, keeping the temperature constant as the two phase flow is occurring, right. But however, if you look at what will be quality here at the 4 of the steam, if I consider the steam at the 4, what will be quality? Is it quality will be 1, or it will be 0, or it will be in between? It will be in between, because of what you call two phase flow. And for expanding the steam, right, in a two phase flow is very difficult, and also it may corrode the blades, right, because of two phase flow is difficult to handle. Similarly, there is a problem with the what you call compression also. And so, if you look at to overcome that problems, right, one can think of solving that problems. How we can solve that problems? What we can do, we can think of this compression, if we can manage to have in this superheated region. This is your superheated region, right, isn't it? And then this portion is your compressed liquid. So, if you do that, then you are handling the single phase fluid, and then the problem may be solved, right. So, if you look at that we can think of, that means like we can add the heat here 2 to 3 and then expand from this superheated region till the saturated vapor region 3 to 4, one can think of. And of course, 4 to 1 there is no problem, because one can do this thing, heat rejections, right. And then of course, it is a liquid here at the state 1, and then you can compress in a liquid very easily, single phase fluid. So, that problem can be solved. But if you look at here, then it is very difficult where to control, like so for example, in the condenser when it is heated, heat being rejected between the station 4 and 1, to what extent it will be, heat will be rejected such that it can go. I mean like I can very happily reject to the saturated liquid condition, but here it can be here, it can be here, it can be anywhere in between. So, then if you do that, then that you cannot have a control over the even compression to till what extent practically if you look at. But in the modified version of this Carnot vapor cycle, you will also find in this region between 2 to 3, right, there will be a problem, because pressure, the pressure will be remaining constant between state 2 to 3 in the modified Carnot cycle. This is your modified Carnot cycle. Will it be? No, because each point will be one pressure, like if you look at it goes, this is one point, each one of them will be different pressure. That means pressure is changing, right. You are trying to keep the temperature constant, it is very difficult to manage in a system. So, therefore, this will not also solve the problem. Okay. We may think hypothetically, look, we can solve this problem, but however, we are getting a lot of problem between the heat addition. Earlier, heat addition was a very simple process in the Carnot cycle, that is 2 to 3. If I keep this pressure constant, temperature automatically remaining constant, isothermal. Here I cannot keep this 2 to 3 constant pressure, and then if I will vary this pressure, then temperature also will change. So, it is very difficult to keep the isothermal heat addition between state 2 to 3. This is a problem. So, and of course, that is the problem we will be addressing, like how to do a practical vapor power cycles. So, if you look at the efficiency one can determine thermal efficiency W net by Q1, and we know that there is W net nothing but Q1 minus Q2 divided by Q1, and this Q1 we have seen that is basically what you call Q1 is T1, this is your temperature T1, right. This is your temperature T1 and this is your temperature T2. So, T1 SB minus SA, right, minus, and this Q2 is nothing but T2 SB minus SA, and divide by T1 SB minus SA. So, if you cancel this out, you will get the Carnot efficiency is equal to 1 minus T 2 by T 1. This we have seen, I am like that basically it is dependent on the two temperature, one is what you call sink temperature T 2 and the source temperature. So, what happened, like whether we can solve this problem, what we will do, we will instead of this compressor, what we are doing, we are basically replacing with a pump. This is a pump. You know what is the difference between compressor and pump? Pump is generally will be handling the liquid, like we use water pump and other things. And the cycle is similar in nature, right. I am like there is a boiler component, there is a turbine, there is a condenser, only instead of compressor we are replacing with the pump. That indicates, that means in the condenser the liquid will come to the saturated from the vapor, it will be coming to the saturated liquid point. That means all the liquid, there is no vapor as such. So, and this cycle is basically modified by the W.J. Rankine, and that is why you call this modified cycle as a basically Rankine cycle. So, if you look at the process, what we are doing? We are retaining the same heat addition 3 to 4, that is a constant what you call pressure and also the isothermal heat additions, right. Temperature will be remaining constant. Okay. And it is being expanded in the 4 to 5, that is isentropic expansion we are considering. This is the ideal one, okay. In actually it will be different. And then heat rejected from 5 to 1 till it is what you call saturated liquid, only liquid. That means X in this case will be X 1 will be 0, quality of the steam will be 0, right. And therefore, it is only liquid, and then this 1 to 2 is nothing but your pump work. And then of course, heat addition it will be 2 to 3, right. This will be sensible heating, and then 3 to 4 will be constant pressure heat additions. So, this cycle is basically known as the Rankine cycle, as I told, and it was devised by him, and this is basically we call it ideal Rankine cycle, because the processes are isentropic. In real situation it will not be, both for the expansion between station 4 to 5 in a turbine and from station 1 to 2 in the pump. It is isentropic, which is not possible in real. Therefore, we are calling it as an ideal Rankine cycle. And let us look at what are the problems we will be facing here, if you consider that 4 to 5, that here in this case what will be X, X 4 will be 1, but in this case X 4 means X is the quality of the steam, and X 5 will be lower than that, right. That means it is, if you look at here, this is your saturated state, this will be region where X will be 1, but here it is less than 1. That means, if it is X is less than 1, right, then it is moisture, more moisture will be there. If more moistures are there, that means it will be corroding the turbine blades. Generally, the quality of 0.9 or 10% moisture in the steam is allowed, is tolerable basically for a turbine, but more than that, like steam, more than that what you call the liquid or this thing, that quality less than 0.9 is not advisable, generally it is not being used. So, to avoid this problem of having higher moisture content, then we can use the superheated steam, right. Then how we will go about? That means, instead of heating here, what I will do, I can go with this again, heat it here further and then expand it. So, that is we will be doing. So, what we are doing, instead of here saturated conditions, and what we are doing, we are superheating it to the higher temperature and then expanding, so that if you find this may be lower moisture content, right. So, that we can overcome this problem by superheating the steam further. Therefore, what we get in modern what you call boilers is superheated boiler, right. That means it can produce the superheated steam, and this is of course known as superheated Rankine cycle, you can say. And this is also an ideal process, okay, because the process in the turbine and the pump we have are isentropic, that we have considered. So, we need to analyze this, like which is things we will be doing, we will be learning how to analyze each components, and what we will be doing, we will be applying basically first law of thermodynamics to the boiler and condenser, kind of things. And if you look at which is your boiler in this part, that is 2 to 4 is your boiler, yes or no? This is the heat added. So, if you look at this is your Q in, right. So, the Q in will be basically H4 minus S2, is it right? So, how we have arrived at this, right? We can consider it as a boiler as a what you call control volume system, and then what are the assumption we are making here? The steady state, right. We are making the assumption steady state, and change in kinetic energy and potential energy is 0, right. Steady state, change in kinetic energy is 0 and change in potential energy is 0, and then what else for this? There is no shaft work, shaft work is 0, right. So, then we will land in getting Q in, right, is equal to H4 minus S2. So, similarly Q out, what it would be? It will be H5 minus H1, right. In the similar fashion we can derive from the first law of thermodynamics for a control volume. Is that clear to you? Yes or no? Right. So, what we can get? We can get the thermal efficiency basically W net divided by Q in. Keep in mind that this could have been small one, right, that is the work done per unit mass. See, if you look at this unit, what you are saying, this will be kilojoule per kg, okay. Will it be kilojoule per kg, right, yes or no? Okay. Right. And the thermal efficiency, this will be Q in minus Q out divided by Q in. And what is Q in? Q in we have already seen H4 minus S2, and Q out is H5 minus H1 divided by H4 minus S2, that is your Q in. And the net work done will be basically, the work done here is basically WT, and this work which is going out, you are supplying it basically, this is WP pump, this is your pump work, and this is your turbine, right. So, H4 minus H5, that is your the change in enthalpy, minus S2 minus H1, the change in enthalpy in the pump, right. That is the net work which the power plant will be producing. And if you look at the Rankine cycle efficiency is less than the Carnot cycle efficiency for the same source and the sink temperature, right. Why it is so? Because if you look at this temperature, T4 and T2, there is a lot of changes in the temperature, it is not remaining constant, right. Whereas, the T4 will be remaining constant in case of your Carnot engine, right. Are you getting? So, therefore, if I draw that, it will be something here, this region, what it would be. If I look at the Carnot cycle will be what? Let me just draw it, maybe it will be helpful for you people to visualize. So, that will be my Carnot cycle, this is my Carnot cycle. So, right, it will be from here to there and then do that. So, therefore, the temperature, temperature here this T4 for Carnot, and this will be what you call, you can consider as a T1, right, temperature T1, this for the Carnot. So, therefore, the efficiency of the Rankine cycle will be lower than the Carnot cycle. So, we will take an example just to find out how we can work on that. This example is about the thermal power plant, which is operated on an ideal Rankine cycle and with the steam mass flow rate of 10 kg per second, right. And water is fed to the boiler at 50 bar, it is a quite a bit pressure, and enters the condenser at saturated liquid at 1 bar, right. 1 bar, 1 atmosphere pressure. So, you are operating at basically like a 1/10 of that, and the mass flow rate of cooling water through the condenser is 500 kg per second, which enters with 30 degree Celsius and leaves at 40 degree Celsius. That means 10 degree Celsius difference is there. And we will have to estimate the temperature at which steam enters the turbine, thermal efficiency of power plant, and of course, the power output of the turbine. So, if you look at like these are the cycle which will be being used for this analysis. Ideal case we are considering 1 to 2 is your what you call the pump work, right. This is your pump, and 4 to 5 your turbine expansion, and this is your in Q in and this is your Q out. So, 2 to 4 is your boiler and 5 to 1 2 is your condenser. So, what are the things are given? If you look at the cooling, for the condenser is given 500 cooling flow rate is 500 kg per second, and mass flow rate of the steam or the water in the closed cycle is basically 10 kg per second, and we know that P2 is equal to the P3 is equal to the P4, because this is the constant pressure line and this is at 50 bar, right, and this is at 0.1 bar pressure. You can say that P1 is equal to P5 is equal to 0.1 bar. And of course, the coolant inlet temperature is 30 degree Celsius and coolant exit temperature is 40 degree Celsius for condenser. These two are for condenser. So, we will have to find out T4, right, and we will have to find out also the thermal efficiency and how much work is being produced by the turbine, right. That will depend. We want to find out efficiency also, right. We will have to find out efficiency. Efficiency is basically W net divided by Q in, and that is equal to H4 minus H5. This is your turbine work minus S2 minus H1, that is your pump work divided by the heat input to the boiler, that is H4 minus S2, right. This is H4 and this is your S2. And what is the turbine work? turbine work is basically mass flow rate is given. What is this m dot? M dot is basically 10 kg per second, it is given, and into H4 minus H5, right. We need to find out H4 and H5, how we will go about it, right. If I want to find out turbine work, this is given, this H4 is not known, so also H5. So, how I will go about it? Any idea? How I will evaluate this H4? You know, like we have already given this, right. We have already given this 50 bar, right, and the pressure is given to you, and this what you call, we have given also this pressure, that is 0.1 bar. I can get this point, right, this point I can get, and again from the steam table, right. So, I will find out basically this one, and then let us look at, okay. And we can find out these 2 points? I can find out, because basically we have given this temperature 30 degree Celsius and 40 degree Celsius, and from the steam table at water 30 degree Celsius we can find out that HF is 125 kilojoule per kg, and for water at 40 degree Celsius we can get HF 167.45 kilojoule per kg from the steam table, saturated steam table, right. And we have given that Q dot C, that is the coolant, you know, used for the condenser, is 500 kg per second, right, and into this one, that is HF at 40 degree Celsius and HF at 30 degree Celsius, I will get this amount of heat, you know, that is kilojoule per second kind of things I am getting, right. This is kilojoule per kg and this is kg per second. So, therefore, I am getting this much of power or the heat will be extracted in the condenser. So, the energy rejected by the mass of working fluid, what it would be then? Q out, what it would be? This will be QC, Q dot C divided by the mass flow rate of the steam, which is 10 kg per second, right. So, that is nothing but your 20,895 divided by mass flow rate of steam, that will give me 2089.5 right per kilo. This will be, what will be unit? This will be, unit will be kilojoule per kg, this unit will be kilojoule per kg, okay. Yes or no? Because this is your kilojoule per second and this is kg per second 10, this unit will be kilojoule per second and this is kg per second. So, this second will cancel it out, you will get kilojoule per kg here, and that is equal to H5 minus H1. So, if you look at that, we know this, you know, we can get these properties at H1 very easily from the saturated steam table, and H5 we know from this. So, and as I told just now, the saturated liquid at 0.1 bar and from the steam table we will give HF is equal to 191.83 kilojoule per kg, and that is nothing but your H1. So, and then if I know this one H1 and if I know this, then I can get very easily the H5, right, and we will do that. And of course, we need to know these properties like Hg, Vf, Sf, Sg, all those things we should get the data. And So, as I told earlier that we are basically we know this H 5 minus H 1, that is equal to, this is known, that is equal to 2089.5 kilojoule per kg, and H 1 already we got from the steam table H 1, right. So, this is known. So, we can find out H 5, right. That is H 5 is equal to 2283.3 kilojoule per kg. So, now I know what is H 5 here. At this point I know H 5, okay. And whether we can it is possible to calculate that, we will see. So, H 5, by knowing this H 5 I can calculate what will be X 5, X is your quality, is not it. Why I need to find out quality here? Is it required? Is it required or not? Because I do not know this point, okay, right. I need to find out this. In general problem, what it could have given, that is given the pressure, that is for this thing, and which is already given, and for the superheated steam you have not given the temperature, right. So, if it is given temperature, then this is your superheated steam, this point is your superheated steam, right. So, therefore, you need to find out that, and if you look at like H 5 is known, and H g is already from the steam table, and H f is known from the steam table, and you can substitute these values and get X 5 as 0.8732, right. I mean, you can approximate like as is equal to basically 0.87 you can do approximately. And then I will have to find out entropy, right. And I can find out S 5 entropy is 71.19 kilojoule per kg Kelvin, because I know this S f and I know this S g, I know X 5, and then I will substitute those values and get that. And as I told that we are very much interested to find out this point, because the entropy will be remaining same, that is S 5 is equal to S 4, because this is isentropic expansion. So, therefore, S 4 is equal to S 5. So, we will be using that condition. So, at state 4 we know this is 50 bar, and from saturated steam table we can get SF. SF is here corresponding to what you call 0.3, that is equal to S 3 you can say, and S g is 5.97 kilojoule per kg, right. And if you look at, this is S 4 and S 5, right. S 4 is equal to 7.19 kilojoule per kg Kelvin, okay. Are you getting? So, therefore, we now very sure that this is a superheated steam. See, in the problem it is not given it will be superheated, am I right? Yes or no? In the problem, is it given superheated? It is not given as a superheated steam, right. But however, now we will find that S 5 is greater than S g. Therefore, it is superheated steam. So, this will fall between the, then you will have to find out temperature. What you will have to find out temperature? Temperature is 500 to 600 degrees Celsius. You will find out this entropy is coming, that is what you call 7.19 kilojoule per kg, and you will have to do a interpolation and then get that values, right. By interpolation, if you look at, I will get this that is your 500 to 600 degree Celsius, for 500, this will be the entropy, and then you will have to find out this entropy and this one, and you will find out the delta T is basically 79.4 degrees Celsius, and then the T4 will be 579.4 degrees Celsius. By knowing this one, then one can calculate what will be the H4 and the similar manner, right, because you know that the enthalpy at two different temperature, and that is 500 and 600 degrees Celsius. Therefore, you can get H4 is 3608.97 kilojoule per kg. And of course, the work done in the pump is S2 minus H1, and which is nothing but V into delta P. This is your specific volume. Volume at what point? At station 1, right. This is basically you can say 1 into delta P, and how much it will be? This is what is will be delta P? Delta P will be, this is 0.1, this is 0.1 bar, and this is your 50 bar. So, therefore, that will give me the what you call work done on the pump or work input into the pump. So, if you look at the specific volume is very low, and this V1 corresponding to the saturated liquid conditions, and which you can get this Vf1 from the steam table corresponding to the 0.1 bar. So, you can note one thing, that this is a very small values, 5.04 kilojoule per kg, right. And of course, you can find out what will be the H2, because we need to find out S2, and because we will have to find out thermal efficiency, and that is your Q in, right, and I will have to find out Q out, right, and that is nothing but your net work. You can think of doing that, and that is H4 minus H5, I mean change in this enthalpy between state. Of course, in this case we can find out the net work is change in enthalpy between the turbine, that H4 minus H5, and the pump work S2 minus H1. So, you will get this one, this H4 we have already obtained, right. This is your H4, this is H4, and then H5 already we got from the balance in the condenser, like, and this, if you look at this work, this difference is quite a huge, right. It will be something you can think of around let us say 1400 kilojoule per kg, and this is a very small 5, one can neglect. So, this is a very tiny amount of work which is given to the pump. That means, the turbine is producing large amount of work. And if you look at, if you do a scaling over here, generally this portion is being shown as a little bigger. Otherwise, if I put a proper scale, then it will be very tiny. You cannot see even a diagram. Okay? Therefore, we magnified it and then put it 1 to 2. So, that net work will be by the turbine will be m dot into H4 minus H5, and that happens to be 13.28 megawatt, and of course, this is known like 10 kg per second. So, if you look at the back work ratio which we had defined, that means how much the power being consumed by the pump as compared to the power produced by the turbine, that is Br is equal to Wp by Wt, and if you put that thing, which is very small. We will see whenever we look at some other power plant, we will see it is a very sizable amount. That is the beauty of the steam power plant, that work input to the pump is negligibly small. So, if the steam is produced from a constant thermal reservoir at 600 degrees Celsius, right, and if you look at, we need to find out the second law of efficiency, and the second law of efficiency is basically the net work done divided by the reversible work. We have already seen this Q in into 1 minus T h by T L. Actually, it should be other way around, it will be T L by T h. So, that is basically Q in into 1 minus T L by T h, and this is your nothing but your Carnot efficiency, if you look at that way. And then when you substitute that, you will get 59.1% is the second law of efficiency. What was the first law of efficiency? Can you just look at your note and tell me? It will be something around 38%, right? 38.76% is the first law of efficiency, and second law of efficiency is basically 59.1%. That means there is a lot of scope to improve, the efficiency of this power plant. Of course, we are considering ideal, but still then there is a scope of improving from 38.76 to the 59.1. So, of course, if you look at this Q in, one can find out H 4 minus H 1, and then that already we have done, and then you can find out the efficiency. So, we will stop over here, and in the next lecture we will be discussing about other aspects of the Rankine cycle.